Okay, I'm looking at the theorem. It's copy pasted, or she copied it straight out of the book, but then she used a different form of it. So, oh god. So you have an infinite series, and they can start it at k is equal to 1, which they did, or you can start it as k is equal to 0, as she did. So, oh god. I don't know if I want to go into the details of that, but we actually talked about it where it's geometric series, and there's one form where it starts off at 0, and there's one form that starts at 1, and they're equivalent, but you have to, adapt to the situation. And your book had one and she did the other or something, but the same issue is happening here, because I can literally see the theorem 10.20 in what the thing you sent me, and then right below it, the work that she did, that you said she did, she's using a different form of it to do it. So, oh my god. Anyway, I'll stick with hers. I don't like hers, to be honest with you, but we have problems. No, let me look at what the book problems that you have. Oh no, I have it right here. Because you are doing problems out of the book, and they are all starting at, oh god, some are starting at 0, some are starting at 1. Jesus. Okay, that's going to be a pain. I'll just follow her work for now. Anyway, you do have to adapt to whether it's starting at k is equal to 1 or k is equal to 0. In fact, I am going to go through both. Okay, so you'll have a -1 to some power there. And it could be either k or k plus 1. Your first term could be negative, then positive, then negative. Your first term could be positive, then negative. So the sign of the first term can be different in different situations. It doesn't affect things because all of these are referring to absolute values of errors. So the fact that it's alternating and the signs change won't matter for the things you're doing. You're just going to be finding absolute values, caps on the error term. Help further explain. Yeah, that's what I'm trying to do. I'm trying. Anyway, a generic form of an alternating series can be written like that. Oh, actually, I'm gonna. It could start negative, but I'm gonna write it so it always starts as a positive term. Okay, and so if I did this and I did k is equal to 1, it would be -1 squared, a1. My first term will be a positive a1. Then it'll change signs. When I do k is equal to 2, it'll be a2, but it'll be -1 to the 2 plus 1 is 3, so it'll be 8 minus a2 plus a3 ... The other form, they're starting at 0. They're starting at 0. Sometimes I'll just put a k there so that your first term is positive. -1 to the 0 is going to be positive. And a0 minus a1 plus a2. Okay, so it's off track, like things are just being counted differently. But in both cases, when they refer to Sn, they just want the first n terms. So this is sometimes called the nth partial sum. It is the sum of the first n terms. So it could either be a1 minus a2 plus a3 ... all the way to an 1, 2, 3 ... That's n terms right there. Or, as she's been doing, if you are doing the one that starts at 0, a0 is your first term. Then, to get n terms, you still want n terms for the nth partial sum, you need to stop at an minus 1. And then that's n minus 1 terms up to there, and then an extra 0 term makes it n terms. That is also n terms. So, you do have to kind of keep track of that. And so, actually, let me move that over here. And so the nth partial sum, where you're just summing n terms, not the infinite terms that you would need for the exact value of the series, can be an approximation. The terms get smaller and smaller, so if you do like 8 terms and just chop off the rest, usually you're very close to the actual infinite sum, because A8 plus A9 minus A10 plus A11, they're so small that they're negligible. But the way it works is S, they'll use without a subscript, is the infinite sum. Sometimes they even call it S infinity, but not here. So we'll be using S for the full sum, the infinite sum, the value that the series converges to. It's obviously, well, I'm doing this one over here. A1 minus A2 plus A3 plus dot dot dot. Well, it just goes dot dot dot. Yeah. Now let me throw an A4. Okay, and what you can do is you can write it as S1 plus R1. Is that right? Which form am I doing? Okay, she's doing the A0, so she'll be doing the one over here. But anyway, okay, anyway, this right here is S1, literally the first term. And the remainder, so the remainder is everything else. This is just everything else. So all of this is your remainder 1. You could do, let me write it like this. And I'm not going to do S1, I'm going to skip to 2. S could be written as S2 plus a remainder 2. And what that is S2 is, with this form, A1 minus A2. And the remainder is everything else, plus A3 minus A4 plus A5, dot dot dot. All of it is your remainder term. I could also write the series as S3 plus the remainder 3. And what that means is now S3 is A1 minus A2 plus A3. You're using 3 terms to estimate S. And the error in your estimate is going to be all the stuff you did not add, what she called neglected terms. The things you just were too lazy to add. You just want to do 3 terms and you're done, or you're tired and you want to take a nap. Fine, that means your error is whatever is left, whatever you chose not to include. So it's minus A4 plus A5, dot, dot, dot. All of that is a remainder term. Let me focus on her method, or how she's doing it for her example at least, because that's what we're going to be doing when we work this example. Okay. So here it's a little bit different. Yeah, no. Yeah, okay. So here, I'm going to do the same thing. I'm literally going to do S is equal to S2. And it'll be the remainder 2. And just be conscious that S2 is now A0 minus A1. It's the first 2 terms still, but they are indexed differently than that one. So A0 minus A1, the first 2 terms, meaning your error term, the neglected terms, are A2 minus A3 plus A4, dot, dot, dot. And if we choose to do the third partial sum, use that as an approximation, then you're off by a remainder term. Your error in it is based on the rest. Let me write it out. So you got A0 minus A1 plus A2, and your remainder is everything else after that. Minus A3 plus A4 and minus A5 and so on. Okay, and the issue is when you're trying to do an approximation, should you just use 2 are you going to just using 2 terms? Should you go with 3? Should you go with 4 or more? And it depends how close you want to be to the original answer and how much of an error you're willing to tolerate. So what we generally want is a boundary for that. How many terms, if you want this to be small, let's say how small? Let's say 1/10,000th. You want that to be under 1/10,000th, which is what we're actually going to do. Then you got to figure out how many terms you need. And you need to figure out how many terms you need to get that to be smaller than 1/10,000th. And that's where the remainder theorem for alternating series comes into play. And I'm now just going to, The main thing is you understand that slight tweaking of the indexing can really mess you up. But that the S with a subscript and the remainder with the same script, they always refer to how many terms in that partial sum. Whether you're starting at 1, in which case that subscript is the same as the last term in your approximation, and your remainder term starts at the next term up. Or if you're going with that, and the book uses that, the theorem 10.20 is basically this. If you're doing what she did, where she starts her series at 0, then you have to know your nth partial sum is a sum of all the way up to n minus 1, and your remainder is literally that value and above. So we are going to be sticking with that from now on. I'm going to erase, and I can erase that too. But so that was just a little pre-warning about the fact that some of the series starts at 0 and some of them start at 1. And I would pick 1 and go with that, except that glancing at that exercise sheet that you gave me, some started at 0 and some started at 1, so they do want you to be able to adapt. Alright. Let's look at her problem and examine it. Eventually we're going to get to like... Okay, I have to edit because I actually started to work on her problem, and that shifting of index is actually messed me up, so I kind of effed it up, but I'm going to start clean. But anyway, this is I'm going to do her thing. So we have k is equal to 0 to infinity, negative 1 to the k over k factorial. The reason she knows the actual value is 1 over e is because this is a Taylor series. I don't know if you got to that yet, but you will if not. And based on the fact that we're starting at 0, this is the form of it. If you're starting at 1, then the form of this is Rn is less than or equal to an plus 1 because of that shifting of indexing. Oh, goddamn. Anyway, let me write out a few terms. 0 is going to be negative 1 to the 0 is positive, 0 factorial is 1. Be aware of that. 0 factorial is 1. Plug in 1 is going to be negative 1 over 1 factorial. Let me write factorials. When k is 2, it's going to be positive plus 1 over 2 factorial minus 1 over 3 factorial plus 1 over 4 factorial minus 1 over 5 factorial, and I'll stop it there, plus dot dot dot. Well, I won't stop it there, but I'll put a dot 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 at that point. And this is the infinite series. They call that S. Sometimes they call it S infinity, as in you're doing the infinite partial sum, but other times I'll just write S. Your book uses it just S. Again, we do know the actual value. I believe that's equal to 0.31 over e, but so 1 over e is the exact value. It is provable, not something we're going to do now though. Okay, and let us look at, how do I want to do this? What I can do is, and I don't want to start at the first partial sum, I'm going to just jump to, I'm just going to jump to 3. The actual sum can be written as it can be approximated by the third partial sum. How good of an approximation that is? Basically, the error is going to be whatever is left. And so, S is equal to the first 3 terms plus your remainder term for 3 for your third partial sum. And I'm going to write out these terms. This S3 is the 1 plus minus the 1 over 1 factorial plus the 1 over 2 factorial. Those 3 terms added together is your S3. And to get the actual value, the actual exact values, you're missing negative 1 over 3 factorial plus 1 over 4 factorial dot dot dot. So that right there, let me put a different color. So blue is going to be our approximation, and R3 is going to be your error. Where am I at? Negative 1 over 3 factorial plus 1 over 4 factorial minus 1 over 5 factorial dot dot dot. All of that, the infinite series starting at the 3 factorial and beyond, is what's called your error term, and that plus that is equal to the exact value. But if we use this as an approximation, you're off by this much. So this is called an error term or a remainder term. Let me do another one. Let's So you can visualize it. I can do the fourth partial sum. And then when I do that, that means I'm off. I have a remainder of R4. That means I'm using as an approximation for S. If I use a fourth partial sum, I'm using 1 minus 1 over 1 factorial plus 1 over 2 factorial minus 1 over 3 factorial. We're including that fourth term in the fourth partial sum. And then you're off by 1 over 4 factorial minus 1 over 5 factorial, dot, dot, dot. Okay, and that's your remainder there. And I can do another one, but I don't need to, because at this point I want to use the fact that the remainder term is always less than or equal to the first neglected term, is the way she phrased it. So let me go through these now. So for this R3, using my third partial sum, I know that my R3, I don't know, I could get the exact value by doing all that, but if I'm not going to do all that, I just want to bound for it. My R3, I know is less than or equal to A3. Which means that it's less than, specifically, 1 over 3 factorial. And if I use the fourth partial sum as an approximation for S, that means I'm off by this term. But I know that that remainder, that error term, is less than or equal to the first neglected term, A4, which is that right there, the first neglected term. So that's the idea. And now, the more terms I do, the better and better the approximation. And I want to get it so good that I want this error term to be less than whatever she says. So I'm hoping I would like this to be, oh, let me do a generic one. Let's see, I'm just going to, I don't know how many terms I want to do, but I'm going to write it like this, similar to this. And this time I don't know how many terms there are, but I know I'm going to go 1 minus 1 over 1 factorial plus 1 over 2 factorial. And I'll just put dot, 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 but I'm going to cap it off at, this is not a full-on dot, dot, dot to infinity. This is getting capped off at, well, I got to think again now. 3 terms goes up to 2, 4 terms goes up to 3. So this will be to n minus 1 factorial. Because it's always 1 short, because of that weird shifting of index, because you're starting at the 0 term, which means that the first 4 terms goes up to 3 factorial. The first 2 terms goes up to the first 4 terms goes up to 3 factorial. The first 5 terms go up to 4 factorial. This is always 1 less than that. Your remainder term starts for this particular series, and the way it's indexed here, your remainder term is starting at right here, whatever the n is. So this will be 1 over n factorial minus 1 over n plus 1 factorial, and so on. Actually, the signs I don't know. They're all plus or minuses. I don't know the signs unless I know n. So it could be a minus there and plus there, or plus there and minus there, depending what n is. But I'm not going to get concerned with that. The main thing is using this concept or this theorem. I know that Rn has to be less than or equal to 1 over n factorial. Okay, and that's a crucial thing. And now I can use this, the generic form for an unknown n, to be able to figure out what n needs to be, how many terms I need to sum, to keep my error term, how far I'm off by, to be under a certain amount. So let's start working this problem now. I want my error term to be less than 1/10,000th. Let me jump ahead and tell you what it was again. Okay, so what did I have? R3. It's less than 1 over 3 factorial. Let me see what 1 over 3 factorial is. 0.1667. So I know if I use the S3, the third partial sum, as an approximation for S, I know it's going to be off by an error that's less than that. Four terms is going to be a better approximation. And I know that when I use that as an approximation, my error, I'll be off by an amount that is less than 0.042. Oh, 0.417. I didn't do R5 earlier, but let me just go ahead and do 5. And the goal is I want this to be certain, I want this to be small, and usually there's a cutoff. They say you want it to be less than a certain amount, and here it's going to be 10 to the negative 4. And you'll notice I'm just going up 3, 4, 5, and I'm going to do one more. And be aware, that's ultimately what we're doing. We are actually just 120. This one's going to be less than 0.0083. Okay, so these are the values of 1 over 3 factorial is equal to 0.1667. 1 over 4 factorial is equal to 0.0417, and 1 over 5 factorial is equal to 0.0083. And what I'm using those for is knowing that the error, if I use S3 as an approximation, is less than that. If I use S4 as an approximation, my error is going to be less than that. And the more terms I use, the smaller my error is going to be. I want it to be under 10,000. Sorry, 1/10,000. So let's just go dot, dot, dot. For a generic n, I know my error term, my remainder term is going to be less than 1 over n factorial. And now here's where I'm going to actually use the specification given in the problem. I want this to be less than 1/10,000. So I'll just find the n that'll make this less than 1/10,000. That's 10 to the negative 4, by the way. I think you're good on that, hopefully. Okay, anyway. I know that this is always less than that, and I want this to be less than that, so I just look for this. And you can solve it for n in certain situations, but not with a factorial. You can't really solve for an n factorial. That's not a thing you can do. But if it's like a square root of n or a power of n, you can actually algebraically solve for n, solving inequality. Not for factorials, which is why, and even if you could solve it, it may not be worth the time to do weird things to get n by itself. Sometimes it's better to do trial and error. So that's what we're going to have to do here. But it's probably what you want to do regardless. I already did 3, 4, 5. I'm going to keep going until this is less than that. So I'm no longer going to write the whole thing, but I'm going to focus on this. I'm going to start over here, and I'm going to start breaking down. 1 over 5 factorial is equal to 0.0083. That is not less than that. 1 over 6 factorial. This is what she did. This is why she started listing them out. She kind of jumped to 7 and then 8. Yeah? Oh, and she did a weird thing of... I'll go back to that later. I'll do that afterward. But anyway, I'm going to do it the basic way. I want that to be less than that. I'm just going to plug and chug. 1 divided by... Oh, I'm sorry. Let me just... 1 divided by 10,000 is 0.00001. Is that right? It's elementary school stuff, and I forgot it. How many zeros is that going to be? No. That's right. 4 places. Okay. Anyway, I'm looking for this to be less than that. Nope. Let me do 1 over 6 factorial. Trying to do a shortcut because finding factorial on the calculator is buried in menus. Okay, so that is 0.0014. Nope. Oh, and I should be doing extra places. Let me fix that's 39. So this is kind of what she did, a little bit different from what she did. Okay, this is scientific notation already. 0.00020. Nope. One more. Okay, this one is 0.00025, let's say. Bam! That's the one that's less than 10,000. 1/10,000th rather. This one is not. Nope, nope, nope. So I need at least eight terms. So basically, I can conclude that 8 works. 1/8 factorial is less than that, so that means the remainder 8 will be less than that, which means S sub 8 will be an approximation that is within there. That's it, and is equal to 8. Let me backtrack and just talk about how she solved it. She's probably right, it would have been easier. I didn't think about it, but I was just trying to do the basic of making that error less than 1/10,000th. What she did was, just to clarify, she took that inequality that I had. I want that to be less than 1/10,000. And I said you could sometimes solve for n and manipulate since get n by itself and have an answer. Other times it's going to be trial and error like I just did. But even though I will have to do trial and error, it sometimes helps to what she figured out is it sometimes helps you to rearrange this a little bit for easier things to plug into the calculator. So using your reciprocals and flipping direction or cross multiplying, however you want to think of it as, this is equivalent to n factorial being bigger than 10,000. For this to be smaller than that, this denominator needs to be bigger than 10,000, or manipulating it algebraically. Either way, it would have been way easier, I agree, for me to just start plugging and chugging into this. So I will look at n is equal to 5. Is 5 factorial greater than that? 6 factorial, 7 factorial, 8 factorial. And I did this, this is 5,040. This was 720. This one was 120. And none of those is bigger than 10,000 until you get to 8. 50, 40 times 8. Right there, and we got 40,320. And so that's the one that is actually bigger than 10,000. So that's what she did, not doing literally this like I did. She manipulated a little bit so it would be easier to plug into a calculator and do the test things. Which, in retrospect, I absolutely agree with. Anyway, we need to use 8 terms. That's what she wrote. Yep, I agree. We need to use 8 terms. Which means that 1 minus, let me write S8, which is equal to 1 minus 1/1 factorial. That's 2, 3, 4, 5, 6, 7, 8. Using that as an approximation, will be very close to the actual value. That it'll be within 1/10,000th of that actual value of 1/e. So that's the idea. Okay. So 1/e is equal to all of this plus some error term. And that error term I can guarantee is under 1/10,000th. That's it. Yeah, that was iffy. Okay.